I guess so I'll get started with with launching this. So hello everyone, and thank you for joining. So I'd like to welcome you to the second session of our fall program for VISIM. And today we'll have Hanna Power and Yuto Nakazato presenting their work. So just a reminder that each presentation should be about 20 minutes, and then we'll take questions from the audience for about 10 minutes for each presentation. So really people can speak their questions or send them using the chat feature, and I can read them out aloud for everyone. And so just looking forward to the presentations and the interaction. With this, I'd like to present our first speaker. Hanna Power is a PhD candidate in the Civil Engineering Department at the University of Delaware. She works with Dr. Trip Shenton, researching retroreflective sheeting materials and their potential use as passive strain sensors for structural health monitoring. Hanna holds a bachelor's and master's degree in civil engineering from Villanova University, conferred in 2016 and 2020. And before coming to the University of Delaware, Hanna worked for Michael Baker International for 4 years in the greater Philadelphia region, designing and rehabilitating bridges. So with that, I'd like to hand it over to Hanna.
Thanks. I'm just going to share my screen.
Yeah, thank you.
You did announce that we are recording. I think that's it.
Oh, yes. Yeah. It should say it right when you join, but yes, we are recording. So I hope that's okay with everybody. And these will be uploaded. So.
Okay. Do you see the presenter view? You see the correct view of my screen?
Yeah, that's right. Mm-hmm.
Okay. All right, so thanks. As Adrian said, my name is Hanna Power, and I'm a PhD candidate at the University of Delaware in the Civil Engineering Department. And my research is into passive strain sensing for structural health monitoring using retroreflective sheeting materials. So here's an outline of everything I'll talk about today. I'll first introduce retroreflective sheeting materials and how you measure their retroreflectivity. And then I'll move on to the materials that I've been working with and testing. And then I'll get into all the tests that I've run so far, which includes tension, strength, some variability tests, a little bit of exposure testing so far, and a microscopic evaluation of the materials. And then I'll move on to how you would actually install a sensor made of retroreflective sheeting materials. And I'll just wrap it up with some conclusions that we've come to so far in this research. So first, retroreflective sheeting materials, they're almost fabric-like materials that are reflective in nature, and they're used mostly to make traffic signs. You can also make raised pavement markings with them, which is what this photo is here. And ASTM standardizes a couple different types of RRSM, but they're produced by a range of companies, and all of these companies use various technologies to ensure that RRSMs are reflective so that signs and pavement markings can be clearly visible. So the different standardized types of RRSM can be made a couple of different ways. And here you see two different standardized types of RRSM. On the left-hand side, we have a type 1 material, and on the right-hand side, we have a type 11 material. A type 1 material is a lower grade material. It's a little less efficient, has less ability to reflect light, whereas on the other hand, a type 11 material is considered more efficient and reflects light better. So a type 1 material is made of a layer of glass beads. That's what these blue circles represent. And the glass beads are actually backed with metal. So they're referred to as metallized RRSMs. Whereas on the other hand, a type 11 material is known as a prismatic RRSM, and it is made of these prisms. And the prisms actually do all of the reflecting within themselves. So there's no metal. So these are called unmetallized RRSMs. So you can see the difference in the way the light is reflected in these two schematics down here in the bottom. Here, this arrow with the gray line, it represents a beam of light. So here, a beam of light will enter the glass bead and actually bend or refract within the glass bead. And the metal is what does the reflecting. Whereas in a prismatic RRSM, all of the light is actually reflected within the prism and returned to the source. So these two images down here are images that I took with a microscope of a type 1 and a type 11 material, and they really show the two different types of reflecting layers you can have. You can see the glass bead makeup of a type 1 material. These circles are the glass beads. And on the other hand, this is a type 11 material, and you can see the prism makeup. So the amount of light that these RSMs are able to return to their source is known as retroreflectivity. And retroreflectivity can be measured a couple of different ways, one being using a handheld retroreflectometer, which is what you see in the photo here. And many DOTs own and use these reflectometers regularly to measure the reflectivity of their signs, because the FHWA has a requirement for minimum levels of reflectivity of their signs to ensure that they can be seen by the public, right? So DOTs and other sign owners actually make their own signs. So they own these RRSMs and they're very familiar with working with them. And then they also own and use these retroreflectometers because they need to uphold compliance with the FHWA minimums. So both of these technologies and these materials are very familiar to sign owners and therefore bridge owners like DOTs. So we're hoping that this technology is using these as strain sensors will be a pretty easy transition. So my research is into relating that measurement of retroreflectivity in retroreflective sheeting materials to the amount of strain that is induced into a material. So here's a list of objectives that I have for my research. First, I need to understand how RRSMs and the various types of RRSMs respond to applied load within the context of using them as a passive strain sensor. Then I need to develop a relationship between retroreflectivity and microstrain for all the different types of RRSMs. I also need to determine the basic material properties of RRSMs. And then as we implement these as strain sensors, they'll be exposed to the environment. So I need to characterize how exposing them to the environment changes both their adhesion and their retroreflectivity. I also want to examine why we see changes in retroreflectivity as we load these materials. So what mechanism is changing as we load them. And finally, I need to develop a process for taking these rolls of material that they use to make signs and implementing them as strain sensors. So I'll introduce a couple materials that I've tested. I've actually been working with 10 different materials, but in the interest of time, I'm just going to talk about 4 here today. So I've tested materials manufactured by both 3M and by Avery Dennison. And you'll see I'll talk about 3 different materials manufactured by 3M and 1 by Avery Dennison. And as you remember, this type 1 material that's designated 3MTI throughout the presentation has that glass bead makeup, whereas the other 3 materials have a prismatic layer. There's different types of prisms, so they do vary a little bit in the makeup, but they do all have prisms, so they're all unmetallized materials. So the first test that I ran on these materials were just some basic tension tests. I adhered a strain gauge to the back of a dog bone shape of all of these specimens. The backside is non-reflective, so I put a strain gauge on the back and hooked it up to some data acquisition software, and then I loaded the materials in tension and I took retroreflective readings so that I could compare the two. So here's a schematic of my loading protocol. So each specimen, I did 3 specimens of each type of material, was loaded through 3 runs, so 3 loading and unloading cycles. And you can see these little plateaus here in the loading and the unloading cycles. And those are because I actually had to manually pause the loading to take retroreflective readings. So in order to get an accurate retroreflective reading, the reflectometer needs to be flush against the surface so that all light is closed out. That's the only way to get an accurate reading. So that's what those plateaus are. I needed to pause the load, and I took a couple of reflective readings along the length of the specimen and averaged them because, as I'll talk about in a little bit, there is some variability in the readings. So the next couple of slides that I'm going to show are going to be results from these tension tests for those 4 materials that I just talked about. And what you'll see is in red, I'll have highlighted the first run and the last 2 runs are in blue. And the reason that that first run needs to be called out and is important is because we need to evaluate if these materials degrade with cyclic loading, right? So if we implement these as passive strain sensors, they're going to see cycles of loading, and we need to ensure that those cycles of loading don't degrade the reflectivity so much that we can't get an accurate reading of strain when we take a reflective reading. So this is the first material. This is a type 1 material. It's made up of those glass beads and a metallized backing. And you can see the first run, it has a somewhat linear relationship between retroreflectivity and strain. But then as I continued to load and unload the material, the retroreflectivity went almost unchanged. So this one really degraded. As soon as we loaded it, the retroreflectivity degraded and we were never able to get it back up to its initial retroreflectivity. So while this material has its purposes, it's not going to be a great candidate for being used as a passive strain sensor. So the next material that I tested, this is a type 4 material. So this has a prismatic reflecting layer. And you can see this is very different than the type 1. The retroreflectivity strain relationship is really linear and it's tightly correlated. And the first run doesn't differ very much from the second and the third runs. So those were all things that we considered when determining if this would be a candidate for passive strain sensing, as well as some other tests that I'll talk about in the future. But this is more the relationship that we were looking for when we did these initial tension tests. So this is a little bit different than the two that I've shown so far. It's not as linear as the type 4 material, but it doesn't degrade nearly as much as the type 1 material. So again, this is a prismatic RRSM, and you can see that this almost has a bit of a sag curve to it. So we've only done linear relationships so far, but we are going to look into using some different relationships between retroreflectivity and strain for certain standardized types of materials. It may fit better to a different relationship. And similarly, this is a type 11 material. This has a much tighter scatter than the previous one that I showed, the type 8. But again, a linear fit might not be the best. This one might actually be best fit to two different equations. One possibly for the first 1,000 microstrain might be a curve here and then a linear relationship. So that's something we're going to explore in the future too, is writing different relationships for certain materials depending on what range of strain and what range of retroreflectivity you're seeing. So the next test I did were some strength tests of all of the materials. So I used the same machine that I did for the tension tests and dog bone shapes. And I just loaded every material to failure. I recorded the maximum load and the total extension, and I also measured the cross-section of each of the materials. So I was able to calculate the failure stresses and strains of all of the materials. And that helped us to determine if these materials are viable to be used as strain sensors, particularly on structural elements and bridges, because we needed to ensure that they wouldn't break if they saw the strains that these bridges typically see. So this helped us in determining that some of these materials are viable to be used as passive strain sensors and which are more viable than other materials. So like I had mentioned before, these RRSMs, you do not get the same reading of retroreflectivity when you take multiple readings on the same specimen. So I wanted to quantify what that deviation was and what I can expect that to be. So what I did was I cut just 1 square foot of every material and I took 100 readings over the surface of the material and I calculated the average base reading of retroreflectivity for each standardized type of material. And then I also calculated the standard deviation, which is what these bars are, and from that I could get the coefficient of variation. And the reason that I needed to do this was to determine if I'm getting a change in retroreflectivity as I load this material. I need to know if that difference in retroreflectivity can be attributed to just its innate variability, or if it can be attributed to the strain in the material. So again, this was a parameter that we considered when we were deciding which of the materials would be best to use as passive strain sensors. So this is an ongoing test that I have, some exposure testing set up outside. Right now, we're only testing type 11 materials. We just started with this, and you can see I adhered some type 11 materials to a steel plate and to a concrete block outside. And we tried a couple of different adhesion methods to determine the best way that we're going to get these to stick to common substrate. So it's clear on the concrete here, we skim coated it with some epoxy, and up here we did not. So we're trying some different adhesion methods. And what we do is we go out every couple of months and we pull off strips of these materials and evaluate how the adhesion is changing. And I also take retroreflective readings to determine how the continued environmental exposure is affecting that retroreflectivity. So the variability tests actually really helped with the exposure testing, because now I know how much change I can expect in the material based on its variability, or I can determine if changes I'm seeing in retroreflectivity are due to this continued weathering. So this is a test we have ongoing. And like I said before, we've been able to determine certain materials that are most viable for passive strain sensing. So we'd like to test all of those for exposure as well. So that's a future test. So the next test I'm going to talk about is some microscopic evaluation that I have ongoing of the materials. So as we started to do the tension test and realized that as strain is induced in the material, that we get changes in retroreflectivity, we started to ask, well, why does that retroreflectivity change? What in the material is changing and giving us those different readings? So I thought looking at it under a microscope would help us to better understand that. So here's my test setup. This is the microscope here. It's just a handheld microscope and it has a camera on it. So I actually made videos of loading all of these materials to failure. And I paused the load at every 5 pounds and took screenshots of the video. So I was able to evaluate how the material was changing as it was loading. So then what I did was I actually was able to measure a grid pattern that some of these materials have overlaid on them. I'm not sure how clear it is in this photo. Excuse me, how clear it is in this photo, but there's a grid like pattern. Here's the one square, here's another square, and so on. So actually Avery Dennison is the only one that does this grid pattern. So that's the only type manufacturer they've been able to do this test with so far. But what I did was I measured the dimensions of these grids at different loads. And from that, I was able to calculate strains. So in the table here, you can see the strains that I calculated are in this column, and I compared them to strains that I measured with the strain gauges that I used during the tension tests at the same loading of the same material to see if I could calculate similar strains to what I was actually measuring with the gauges. And if you look at this type 4 material, you can see the strain that I calculated, for example, at 5 pounds was 994, and the strain that the gauge measured was 970. So they're very close. They're very close to one another, which helped us to determine that we believe the prisms are what's doing the straining. So the angles of the prisms are changing, which is changing that measurement of retroreflectivity. So this is something we have ongoing and we'd like to keep exploring. One of the issues with this test is that as the specimen is loaded and the microscope is set in one place, the frame of the image that we're looking at is not the same. So this actually moves as the specimen is loaded. So we're not measuring the exact same points on the grid. So it's not a perfect science that we have here, and this is still an ongoing test, but it's initial indication of what's happening within the material that's changing the retroreflectivity. So finally, I'll just talk a little bit about how you would go about using these materials and installing them as sensors. So these materials come on these large rolls. As you can imagine, they need to be very large to make a traffic sign. So first thing, you want to just cut a more usable size of the material down and template a small dog bone specimen. And once you trace that out, you can actually just cut this material with scissors. It's quite easy to cut. And then once you have a dog bone specimen patterned out of the RRSM, you just want to shave the ends to ensure that no readings are taken within the ends of the dog bone specimen. You want all of the readings taken within the gauge length. So then these are actually some photos of me installing one here. So the first thing you want to do to your beam is wire brush it and really clean it to make sure that you can have good adhesion between the RRSM and your structure. So here I'm wire brushing it, and then I cleaned it with another brush, and then I actually used acetone to make sure there's no debris on the surface of the beam. Next, you just want to mix some epoxy. This is a concrete beam, so we used epoxy. We used an epoxy coating before we adhered the sensor. So you mix some epoxy and just skim coat it. You want to wait for that to cure and dry and make sure it has no tackiness to it. And then these RRSMs are actually, they have an adhesive backing. So you just pull off the film to expose the adhesive backing and put it where you've cleaned the surface of the beam, where you've epoxy coated it. Next, you can see me rolling with a rubber roller the sensor onto the beam to, again, ensure good adhesion. And I'm just using a paper towel as a barrier method to assure that no debris gets onto the sensor so that we can make sure that our readings are accurate. And then I went up with my retroreflectometer and took initial readings. And that's what you can use to calculate your strains once we get the equations correct for every type of material. And hopefully you can use that to be able to determine if something has changed. You'll be able to use your retroreflectometer in the future to go up and take readings. And hopefully your readings will indicate if any strain has been induced into the beam. And this is just a final photo of what the installed sensor looks like. So to wrap up, just some conclusions of the research that we've done so far. It's been apparent that certain types of retroreflective sheeting materials, they are sensitive to strain and they do show promise for use as a sensor. We've also determined we need to continue our exposure testing to evaluate how these materials change with continued weathering. How does their adhesion change? What is the best method of adhesion? And how does the retroreflectivity change with continued weathering? From our microscopic tests, we've been able to determine that that prismatic layer that does the reflecting in the RRSMs is actually straining as we put load on the material. And we've also determined that implementing RRSMs in this way, it's going to be very simple. As you can see, the installation is not complicated, and it's actually going to be quite inexpensive because, like I said before, bridge owners actually own the RRSM materials that they make signs with currently, and they own the technology and have working use of the technology to measure retroreflectivity. So it's going to make implementing this material as a passive strain sensor quite inexpensive. So if anybody has any questions, I'd be happy to try to answer them.
Thank you. That was really great. I guess if no one has a question, I have kind of like a question of my own. So I thought this was really, novel, using what is out there for something like repurposing it. Is always a good idea, I think, especially in the sense of like the motivation that state DOT is already used to using not only the instrumentation to measure retroreflectivity, but also like the actual sheets themselves. Though so I see the motivation and the reasoning behind classifying existing materials, but do you think there could be greater benefits by designing materials, retroreflective materials, specifically for passive strain sensing? So maybe like a more dedicated design such that certain components of what you were talking about, like variability and strength, like meet the needs that you would want.
Like designing a new composite material almost for this purpose rather than using one that's already made. I'm sure that would probably give us better results. If you look, let me go back to like a plot like this, for example. This material that's already been made gives us a very linear, tightly correlated relationship between retroreflectivity and strain. But something like this has a bit more scatter, has a bit of a sag curve. You're not going to be able to write a relationship that's going to be extremely accurate, right? So developing a new material, I think, is a great idea. But like you said, the beauty of this is that we actually think a DOT might be willing to implement it because they could use the material they already have in the back. They wouldn't have to buy anything new, learn any new technology. So I don't think that's within the scope of this research. It's not a bad idea, though, to develop a material just made for passive strain sensing. Part of the variability is just what's natural in the material. I don't know that would ever go away. I'm not familiar enough with retroreflectivity as much as I've researched it. I'm not sure that you can ever use this, where is the tool? This tool to get super accurate readings. So there are different ways to measure retroreflectivity. ASTM standardizes various ways to measure retroreflectivity. This is a handheld way that DOTs use because it's portable. So this is a rechargeable battery, and I just put a strap over my shoulder and can carry this out onto the site with me. So that's the beauty of using this tool to measure retroreflectivity. But its downfalls are that it's not as accurate as using some ways where you could do it in a lab, right? Because like I said, you have to close out all light. So we have this aperture to reduce the amount of, to reduce the size of the hole that we use to measure the light source. So it's not a perfect way of measuring retroreflectivity, but again, what we're going for here is simplicity and inexpensiveness, right? So I do think developing a new material would be a great thing to research, but to the goal of keeping it simple and inexpensive, I don't think that would fit that part of this research goal.
I have a quick question, Hanna. I think this was a great presentation, and I think that time and again you were answering my questions as you went along, and so I thought it was good. I do have I have a few questions. So I'm not sure that you talked that much about other possible applications. I mean, initially, I thought that these might be used to monitor transportation infrastructure, and I was going to ask if you would use it for health monitoring or perhaps for weigh in motion, that sort of thing, right? But then a couple of things that came up now in your description, right? When you were discussing the handheld reflectometer, I think that couple of things. And so one, in terms of cost, how does the cost of, because you need to have the dedicated reflectometer that is installed, right? And so how does that compare? So I guess the material itself is cheap, but how does the cost of the reflectometer compare to what would be like kind of having an embedded inexpensive strain gauge? And
Right.
and the other question that I have is, I wonder if if in addition to the measurement error induced by essentially the variability in terms of locating the handheld device, I wonder if there are other environmental factors that might affect or that might result in measurement error.
Right. So, okay. So to answer your first question, these handheld sign retroreflectometers are not inexpensive. They are quite expensive. We do not even own one. I currently am borrowing one from the city of Newark. They've been very kind enough to let me borrow it. So they are not inexpensive. You have to factor that in. But with that being said, many municipalities that own signs also own these reflectometers because they have to report to the FHWA how their retroreflective readings of their signs. So the FHWA MUTCD has a whole list of requirements for sign retroreflectivity. And there's been a lot of research, particularly in transportation, into how retroreflectivity degrades with continued weathering and especially UV exposure. So these signs over time, they degrade and they become less reflective. So municipalities have to go out and measure retroreflectivity and report back to the FHWA saying our signs can be seen by drivers. We don't need to replace them. And most of the municipalities use this Road Vista 922 handheld sign retroreflectometer, and they own it because that is a process that they go through regularly. They own many signs, and it was cost effective enough for them to purchase one. So anyone who owns a bridge, I am working under the assumption that they also would have access to one of these handheld sign retroreflectometers. If they were to implement these strain sensors, my thought is that they have this technology. They're not undergoing the cost of purchasing one of these retroreflectometers because it is not cheap. It is a cost you'd have to undergo. Whereas, like you said, a strain gauge is not very expensive. And then what was your second question? Sorry, I forgot.
No, so thank you. What would you envision as far as applications in transportation? Out of curiosity, do you think that these materials could be used essentially for structural health monitoring? Do you think weigh in motion? Just out of curiosity, what do you envision as far as application?
So we're looking at structural health monitoring, but a couple different applications within structural health monitoring. So we think it can, one, obviously be used as a passive strain sensor. So you implement one of these sensors, you measure retroreflectivity. Ideally, there is an equation relating retroreflectivity and strain. You get your retroreflective reading, you can calculate what the strain is within the beam, right? So that's one application, that's our main focus. We also think that there's other applications, such as measuring crack growth. So you could place a strip of this RSM over a crack, measure the retroreflectivity, and then come back as the crack is growing and measure the retroreflectivity again. If you get a reading that falls outside of that variability that's innate to the material, then you know your crack is growing. Ideally, as we continue to research, we'll be able to write an equation very similar to the retroreflectivity versus strain equations that we have written between retroreflectivity and crack width. So we see it as being used in other applications like that. We also see that it could be used to monitor something like a dead load induced on a bridge. These readings that we see don't change enough with little strains, so we're not quite convinced that they'll be able to monitor live loads on bridges and buildings and things like that. But we do think that it could be used just to monitor the amount of dead load induced onto a beam. and other applications in structural health monitoring. But yeah, we're just focusing on structural health monitoring applications right now.
Okay, great. If there's no more questions, then we'll move on to the next presentation.
Thanks.
So thank you again, Hanna. And so I'd like to introduce Yuto Nakazato, who was originally born in Tokyo, but spent his lifetime till high school in Shanghai, China. Yuto returned to Japan for his bachelor's degree and has been studying at Tohoku University in Japan for 7 years. Now, as a first-year PhD student, Yuto studies infrastructure management under Professor Mizutani's supervision, and his main research interests lie in optimization of repair policies and repair schedules for large-scale infrastructure systems. So with that, Yuto, thank you.
Hello, everyone. So can you hear me now? Okay, thank you. So let me start my presentation. Today, I'm going to talk about the optimal daily repair schedule for road network. So this is about asset management for the infrastructure. So in this, I think in the field of infrastructure management, research about daily repair schedule for road network is also required. So what is the daily repair schedule network? For example, let's consider a toy network with 4 sections and 4 links. By the yearly repair policy, for example, the long-term repair policy or repair schedule, we got the links, the sections have to be repaired in the year, and we have the repair cost parameters. So by then we have to decide which sections to repair on each day. So the daily repair schedule means like 365 days of which sections to repair. And so one of then let me introduce why the repair schedule for the road network is required. When we consider repairing the road networks, road sections for the road network, the repair cost for road network usually consists of 3 types of the cost. First is a variable repair cost, which is proportional to the number of the repaired unit sections. For example, the repair material cost. Second is a variable work zone cost, which is proportional to the number of the unit sections in a single continuous work zone. The third is a fixed repair work zone cost, which is proportional to the number of continuous work zone sections. And for example, the fixed machine cost is a typical fixed repair and work zone cost. So if when only one section on the road is going to be repaired, so we see one unit of variable repair cost, 1 unit of work zone cost, and 1 unit of fixed repair work zone cost is required. But if 2 sections are repaired simultaneously by a same machine, we can reduce the fixed repair work zone cost. So in order to reduce this the fixed repair cost, we can also consider to take the sections that do not need repair into the work zone so that we can repair those 2 nearby sections in one same continuous work zone with one same construction machine. So besides the repair cost, the user cost of the network also changes according to the repair. The user cost of the network changes according to the OD demand and the traffic capacity. And the traffic capacity of the network may changes according to the work zone of the entire network. So here is an easy example For example, all the 4 links with capacity 10 and the network capacity is 20. So when the sections, when links are in the work zone, maybe half of the road cannot be passed. So the link capacity may become half, and the network capacity of the entire network capacity may decrease. So in order to reduce the repair cost, we have to make more sections in the work zone. But if there are many work zones, the capacity of the entire network will seem to reduce. So we have to calculate what is the optimal repair schedule mathematically. About the previous studies, first, this study is considering the use, not only the user cost of the network, but also consider the economic effect of the area by the constructions project. However, this study targets on a series of large constructions. So the construction projects are link-based, not actually 100 meter section space, and it only consider not so many projects. So and don't consider user the repair cost. So it may not be useful for the yearly management of the road network. And another previous study is my study. It's about, it considers the economies of scale in the repair costs, and but it's about the management for a corridor road, not the network. So we didn't consider user costs in this study, and it is solved by a heuristic method. For example, if we have these three parameters, heuristic algorithm parameters, and this corridor network, the sections to repair and the sections to in the work zone are decided heuristically. So the target of this study is to find optimal daily repair schedule for the road network, and considering both the repair cost, which has the economies of scale, and the user cost that will change according to the structure of the network. And the schedule is daily level and 100 meter section level problem. And the user cost and the repair costs are formulated in the linear form so that it can be easily solved. So this is the optimal repair schedule problem. Objective function is to minimizing user cost and the repair cost in the year. And the sections to repair must be contained in a work zone. So the repair costs here, the sections need repair is already decided by the long-term yearly schedule. So here we only consider minimizing the work zone cost and the fixed repair work zone cost in repair cost and the user cost. The repair cost, it consists of variable work zone cost and the fixed repair work zone cost. And here, the number of continuous work zone is calculated by the number of work zone node minus number of work zone. The number of work zone node means the number of nodes that connected to the repair links. For example, if only one section as one continuous work zone is repaired, the number of work zone node is 2 and the number of work zone is 1. So the number of continuous work zone is 2 minus 1 and it's 1. And if two sections are two continuous sections are in the same work zone, the number of work zone node is 3 and the number of work zone is 2. So the number of nodes, number of continuous work zone is 3 minus 2 and 1. So in this way, we can, the economies of scales can be calculated in a linear form. And here is the user cost. So it's a very easy form, which is a minimum cost problem. So in the traffic, I know there are many types of the many types of equations to calculate user costs, but here we are using the easiest form because it's in a linear form, and we are not doing the exact traffic assignment. So because it's a minimum cost for a problem, and if the OD demand exceeds the network capacity, the excess user give up their trip, and a relative high cost proportional to the number of users give up the trip incurs. So here is the network for the numerical study. And these are the parameters using the numerical study. And in the numerical study, we first divide all the links of the networks into a 100-meter sections, new links, and then decide the sections to repair in the year randomly and as a yearly repair schedule, and then compare these two types of daily schedule. First is to repair sections randomly at any date. The second is to apply the optimal repair schedule that's calculated, and then compare the user cost and the repair cost. So here is one sum of the results of the optimal repair schedule, and this is the repair schedule of the day with most repairing sections in the year. So as we can see, like more than half of the links are doing the repair works. So for example, in terms of this link 1 to 12, link number 9, link 1 to 12 is 9 miles, and it's divided into 145 sections. And sections in the work zone are like this. And here is a comparison of the costs of two types of repair schedule, the random schedule and the optimal schedule. So you can find that both the repair cost and the user cost are reduced by the optimal schedule compared to the random schedule. And here the number of work zone increases and the number of continuous work zone decreases in the optimal schedule, which means the more sections are repaired in a same continuous work zone so that the fixed repair cost is reduced. But even though the number of work zones are increased, the user cost, the user give up trip and the user cost is not decreased compared with the random schedule. So 100-meter section level and daily level optimal repair schedule problem is formulated as a linear problem. And I'm sorry, I forgot to say that the problem is the optimal schedule is calculated by Groby optimizer, and we can and in terms of the Gaussian network, which is divided into almost 2,600 links, the calculation time is about 90 minutes, and as a result, the repair cost and the user cost can be reduced together compared with like doing decide the daily repair schedule randomly. So here are the future tasks for this research. The first is model level changes. So first is to add constraints in number of continuous work zone in zone or number or add constraints of number of the length of the continuous work zone. So in the result, we saw that in the day with the most sections repairing in this picture. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 continuous work zones in one link. So there are many construction works doing in only one day. I think it's maybe not realistic. So maybe there need another new constraints. And the second is to ignore economies of scale of repair costs in different links. Now I'm considering the repair for sections nearby that are in different links. So for example, the sections in the link 9 and the sections in the link 7 are repaired. Some nearby are repaired simultaneously. The fixed cost can be reduced. However, maybe in most cases, the cost cannot be reduced. So by cut off the economies of scale in the link, I think the problem can be more easily and it can be more easily solved. The problem can be divided into like link level model and the sections in link level problem. And the second, another future tasks are objective level future tasks. For example, now we consider that the year the sections to repair in the year is decided at the beginning of the year, but maybe in some road networks in Japan, the sections to be repaired in the next year is updated daily. So I think the model can be extended to this kind of problem. Second is considering the cost leveling of the repair costs in the year, or like considering the urgent repair and the insurance budget in the year. And the final future task is about management framework level. So for example, like the joint optimization with long-term repair policy problem. So when we consider optimal repair policy, when we consider management for networks, there are many factors we have to consider, not only the user cost and repair costs, but also like economies effects on the other area, the cost leveling and the green gas emissions, and there are many facts we have to consider. So if we can like divide the problem into a year level repair policy problem and problems that decide the day level repair schedule from the year level problem results, maybe we can like divide those factors into different levels so that the problem, both level problem can be more solvable in an easy way. So here is my presentation. Thank you for listening.
Thank you. Thank you very much, Yuto. So are there any questions from the audience? Oh, yeah, Aditya, I see you have a question.
First of all, I mean, thank you for staying up so late into the night. I know it's, I don't know, 1:30 or much later. So I completely, I appreciate your initiative in staying up in order to share your work. Very nice to see, very exciting work. One question that I had was, so notion of, I guess a couple of related notion of embedding how you traffic within this space. One was the extension of this in the context of, multiple origins and destinations. How do you think of equity, or, how do you define which part of the network is getting compromised and not when you're looking at it? People are going from everywhere to everywhere else. And I guess one extension to that would be the notion of, I guess, looking at delay on the whole, where maybe everything, depending on how many users are traveling, what's the length of delay and things like that. So what are your thoughts on that in terms of, recognizing the system as a whole and relaxing the single OD definition?
Thank you very much. So yes, I forgot to say that I'm now considering about in urban highway road network. So yes, I'm considering the highway in the urban city. So yes, there are. I think there are actually maybe the final, the absolute management problem may contain, like, for example, an upper highway road network and then downtown in the city network, a two-level network optimal repair policy problem. So it's just too hard for me now. So now I'm considering only one network, which is like highway road network, which don't have too many links or too many road selections and have a relatively steady OD demand and OD demand, and it has to be repaired quite often.
No, it's I mean, it's a useful abstraction. And as somebody who kind of got his dissertation out by using the single origin and destination, I completely buy the concept. But given that you've already formulated these problems in the past for the other paper as well that you presented, the DR Part C1, and you also kind of have these things in place, also it'd be kind of just have good food for thought, at least in terms of future work, to think of how to generalize it further. Thanks again, Yuto.
Oh, thank you. Thank you very much.
I think so. This was a nice talk. I mean, as Aditya said, I think undoubtedly a complex problem to think about. I think that a few things do come to mind which you may wish to consider. I think that there is actually a long literature on work zone scheduling, and it's something that I think might kind of help streamline a few of the things. And I think that interestingly, very close to what you are doing, the resilience literature, a lot of recent literature, and this is tied to what Aditya said, where we may want to consider other concerns as well, such as equity. But in the resilience literature, we are often interested. There isn't this issue of dropping capacity in a continuous fashion, but we do have these basically, we do have a set of activities that we want to schedule on a network, right? And then the question is, how do we schedule these activities to maximize some of these measures in a dynamic fashion? And so like in your case, I guess you have cost as your measure. There could be others, but I think that there are many synergies there, actually, and I think it's something worth considering. And then when you consider the dynamic problem of kind of, as opposed to scheduling a set of activities where you want to decide what these activities are, I think that you may wish to refer to some of the work that Aditya did, where he considered essentially scheduling such activities on some nominal networks. And so I think what you have is nice. I think that looking at some of these other things might kind of inform some directions and studies as well.
Yeah, thank you very much. I think so too. So I'm sorry that I haven't studied much, but now I'm going to research more about the past studies about the scheduling. And also I've been read quite a lot of paper.
Also, it's a nice way to pitch your work as well, right? As for example, I mean, now in the US, there's going to be a lot of recovery from the hurricane. And so definitely there's an important question of kind of how to schedule these repairs to kind of maximize their impact. And so it's just, I mean, I think what you have is great. I think this might help you. This might allow your work to have an even greater impact.
Yes, thank you very much. Yes, I will do more research about the past studies, and thank you very much. The idea about hurricane is we don't have hurricane in Japan, so it's very interesting for me. Thank you very much.
Any other questions for Yuto? Okay, well, in that case, I'd like to thank Yuto again, and really thank you for staying up till so late and giving an excellent presentation. And I'd like to thank Hanna as well for her presentation, and all the audience for the great participation and just engagement. So stay tuned for updates on the following sessions that we'll be having in about 3 weeks, and look forward to seeing you then for the next set of presentations.
Thank you very much.
Thank you guys.
Thank
For
you.
again.
Thank you.
Thank you.